In section 4.6, we're going to talk again about rank and nullity. Now, if you remember from the last section, we know that rank is the dimension of the column space of A, and we know that nullity is the dimension of the null space of A for some matrix A. So rank is the dimension of the column space, nullity is the dimension of the null space. So we did problems like this last time. I would like you to, if you don't have things saved, go ahead, push pause on the video, and find the rank and nullity of this matrix A. All right, hopefully you went ahead and did that. This is one we did last section, but I'll do it again. Basically, I have my matrix A. For some reason, I typed it into matrix B last time. So there it is. And we'd go and put that in row reduced echelon form. And what we see is that we have 3 pivot columns that will represent the columns for, the vectors in the null space. Let me step back for a second. We have 3 pivot columns, column 1, 3, and 5. If I were dealing with the finding the column space, those pivot columns would tell me that columns 1, 3, and 5 of my original matrix form a basis for my column space of A. So 3 pivot columns represent that my column space of A would have dimension 3. So the rank of A is 3. And we can see that the free variable columns numbers 2, 4, 6, and 7, represent free variables in the solution to the homogeneous equation. And therefore, we know we're going to have 4 vectors in the basis for the null space of A. And so the nullity of A is 4. So the simple answer to that question is, in this situation, rank is 3, nullity is 4. Now, we can do those types of arguments for any matrix A. And it doesn't matter what size A is. A doesn't need to be square or anything like that. But when you row reduce the matrix, we're going to end up with pivot columns and free variables. Each pivot column is going to represent a vector in the basis for my column space. Each free variable represents a vector in the basis for my null space. So the total number of columns has to be rank plus nullity. So let me go ahead and prove that statement in a fairly straightforward way, hopefully. All right, so let's take a look at this. We want to prove the rank nullity theorem, or just sometimes called the rank theorem. The fact that the rank plus the nullity has to be the number of columns from A. So if we're going to prove this, we just say, well, since A has n columns, when you row reduce A, you'll notice that each of the columns is either going to be a pivot column or it's going to represent a free variable in the solution to the homogeneous system AX equals 0. All right. Therefore, since each column either represents a pivot column or free variables in the solution to that, well, what do we know about the number of pivot columns? Number of pivot columns is going to be the number of elements in my basis for a column space, number of vectors in basis for column space. I am really down there. And then the number of free variables represents the number of vectors in a basis for the null space. Sorry about that. There we go. Better. So those two things have to add up to be n. So those two things have to add up to be n. It wraps around on me a little bit. There we go. Now the number of vectors in the basis for the column space is just the rank. Number of vectors in the basis for the null space is nullity. So what we get is that this means that the rank of A plus the nullity of A is equal to n. All right, so that's what we get. Number of pivot columns plus number of free variables. Each pivot column represents a vector in the basis for the column space. Each free variable represents a vector in the basis for the null space. So we have rank plus nullity has to be equal to n. All right, rank plus nullity has to be equal to n. So that's how you'd prove the rank theorem, basically. Now, we already sort of have done all the row reduction stuff in the last and found rank and nullity if I were to give you a matrix. So we did rank and nullity when you're given a matrix in the last section. In this section, we did it once already. But where this rank nullity theorem comes into play is when we have to use logic to solve questions. All right, so let's consider this. Let's say a 3 by 7 matrix has rank of 3. Then what is the nullity? Or the following, if a 6 by 4 matrix has rank 3, then what is the nullity? This is not a crazy hard question, so I want you to push pause and just think through this and see if you can come up with the nullity of each of these matrices. Now, in this situation, we have a 3 by 7 matrix which has rank of 3. So we go to 3 by 7 matrix with rank of 3. We know the rank plus the nullity has to be n. Remember, n is the number of columns. So 3 by 7 matrix has 7 columns. That means that 3 plus the nullity of the matrix would have to be 7. Okay, so all we know is we know that the rank is 3, so put that in for rank. We know that the number of columns is 7, so put that in for 7. And therefore, what we know about this matrix is that the nullity of this matrix has to be 4. And that's basically all. Now you can do the same thing with the 6 by 4 matrix. 6 by 4 matrix having rank of 3 means that 3 plus the nullity of whatever matrix it is has to add to 4, which forces the nullity of the matrix to be 1. Okay, so that's the idea of using some logic stuff with rank and nullity. We're going to do a few more of those examples. Not every time are you just given rank. So go ahead and try these 2 problems on your own. Push pause on the video and try the problems. For the first bullet, we have nullity of 4 of the matrix, and the matrix has 4 columns. So nullity is 4. We have 4 columns. So what we would say is the rank of A plus nullity is 4 equals the number of columns, which is 4, which means that in this problem, the rank of my matrix has to be 0. By the way, if the rank is 0, that tells us something about the matrix, that we get the rank, the column space, is the trivial subspace. Okay, so there we go. Now with the other situation, we have a 7 by 9 matrix, and the nullity is 6. So we have rank of our matrix plus the nullity, which we know is 6, has to be the number of columns. So the rank of A has to be 3. All right. So there you go. The column space is 3-dimensional. All right. Again, this rank of A being 0, that can tell us something about our column space, but it tells us specifically that our column space is the trivial subspace, the one only including the 0 vector. All right, so that's just basic calculations. Let's use logic to talk about sort of optimal or least optimal solutions with the rank and nullity theorem. So I want you to push pause on the video and ask yourself questions like this. If A is 6 by 8, what's the largest possible rank? If A is 7 by 4, what's the largest possible rank? If A is 7 by 4, what is the smallest possible rank? So go ahead and push pause on the video and see what you end up with. Now, these types of questions are a little bit trickier because not only do we have to consider the rank nullity theorem, but we also have to consider the actual size of the matrices themselves. So here's what I mean by that. Let's start out with this first one. If A is 6 by 8, what's the largest possible rank? Now, immediately your mind may say, well, rank can be all the way up till size 8. And that's almost possible. Okay, that's almost correct. But it actually doesn't work in this situation. Remember, rank is the number of pivot columns we could get. And if we have a 6 by 8 matrix, the most pivot positions I can have is 6. Notice I can't get 8 different pivot positions. So the largest possible rank of A is limited not by the number of columns we have, but in this case by the number of rows, because that's how many pivot positions that we can get. So the largest possible rank of A is 6. All right? So we have to consider both the rows and the columns for largest possible rank. Now, what if we have, so in this case we had to consider that because the number of rows was smaller than the number of columns. In our next question, let's go scroll down here a little bit. When we're asked what's the largest possible rank of A, well, let's go ahead and make a 7 by 4 matrix and see what we can do. So there it is. I just made the 7 by 4 matrix. 7 rows, 4 columns. Now notice what the largest number of pivot columns we have here is. The largest number of pivot columns we can have is 4 because that's the bound. So in this case, the largest possible rank of A is 4. And that's what we have. So in this case, it was determined by how many columns I can have. In the previous case, it was determined by the rows because, again, we're asking ourselves how many pivot positions can it hold? Okay, so there we go. How many pivot positions can it hold? Largest possible rank of A is 6 in this case. Largest possible rank of A is 4 in this case. Now, by the way, what's the smallest possible rank of A? Smallest possible rank of A. Let's go back to the 7 by 4 matrix. I'm going to copy that. What's the smallest number of pivot positions we could end up with? Well, the answer is 0. There is a possibility that I go to the 7 by 4 matrix and each column is just the all zeros column, and therefore when we row reduce, we don't get any pivot positions. So the smallest possible rank of A is 0. By the way, you can argue that as well. If you said what's the smallest possible rank of A with a 6 by 8 matrix, it's also 0. Again, just take the all zeros matrix, and there you go. So the smallest rank of A is 0. And by the way, when we have rank of A being 0, that means that we just have the trivial subspace as our column space. So I want you to, so hopefully that all makes sense. I'd like you to go on to the next step. Instead of talking about rank, I want you to think of the largest nullity possible and the smallest nullity possible. So push pause on the video and answer these 3 questions using logic like we did before. Hopefully you went ahead and solved these problems. So if A is 7 by 10, what's the largest possible nullity? Well, the largest possible nullity is 10. All right, why that is? Well, if I took a big 7 by 10 matrix, what's the largest number of free variables I could have? Well, I could have up to 10 different free variables and no pivot columns as long as my matrix is the all zeros matrix. So it is possible to have 10 free variables if our matrix is size 7 by 10. So the largest nullity possible is 10. Okay, notice by the way that the largest nullity possible corresponds to the smallest rank possible. So if you go back and look at what we did with the smallest rank possible, we made it the all zeros matrix. The largest nullity and the smallest rank would match up. All right, and vice versa too. The largest rank and the smallest nullity will also match up. So let's go to that side of the understanding. So the next question says if A is a 7 by 10 matrix, what is the smallest possible nullity? So smallest possible nullity, hopefully you got out a 3. Okay, so if I want the smallest possible nullity, then what I want to do is I want to fit in as many pivot positions as I can. And if I try to fit in a bunch of different pivot positions, you'll see that the most pivot positions I can put in is 7. And that's going to leave 3 columns for free variables. So the maximum number of pivot positions I can put in is 7. Therefore, the smallest nullity possible is 3. Hopefully that makes sense. And again, smallest nullity corresponds to the largest rank. So when the rank is a maximum of 7 and we're in a 7 by 10 matrix, then the nullity is at smallest 3. Last question here, we have a 9 by 5 matrix. What's the smallest possible nullity? Well, if you think through this matrix, I'm not going to write it down, but what you'll have is 9 rows and 5 columns, and we can create a pivot position in every single column. So we can create 5 pivot columns. We could create 5 pivot columns and no columns with free variables. So what's that mean? Well, that means that the smallest possible nullity is 0. Okay? So if we can have no free variables, that means the nullity is 0. The null space is only the trivial vector, the 0 vector. So that's basically the idea of using logic with that rank nullity theorem. All right, thinking through how many pivot positions could we have, how many free variables could we have, and so on and so forth. Now, before we move on, I do want to make a couple of observations about rank and nullity and invertible matrices. If A is a square matrix, we saw in chapter 2 there was a bunch of equivalent things to A being invertible. Well, now that we have the idea of column space, rank, null space, and nullity, if A is square and it's invertible, then I know it row reduces to the identity. If it row reduces to the identity, then we're going to have n pivot columns. So the rank of A is n. And since we're an n by n matrix, our vectors are coming from Rn. So I have n linearly independent vectors from Rn. That means that the column space has to be Rn itself. So if A is invertible, then the column space is going to be all of Rn, which means that the rank of A is n. Now, as far as the null space goes, well, if we row reduce to the identity matrix, then you're going to have 0 free variables. So the nullity is 0, and the null space is the trivial space which just includes the 0 vector. So all of those things are equivalent to being invertible. So those invertible things still show up even deep into chapter 4. Now, there's another concept that the book deals with in this section, and that's the concept of row space. Now, we've dealt with the concept of column space a lot, okay? The column space is the span of the columns of A. Well, row space is a concept the book looks at. It's the span of the rows of A. Not a whole lot different than column space, but now we're using rows instead of columns. So if you ask me, what's the row space of A? Well, let's think about this. So the row space of A is going to be the span of the rows. Now, it doesn't matter if you write these vectors horizontally or vertically, but let's pretend I want to write these vectors vertically. So row 1 is going to be 2, 4, 5. Again, you could write that horizontally as well if you'd like. Row 2 is 1, 1, 1. And row 3 is negative 1, 1, 2. Again, that's if I write them vertically. So it's the span of those three vectors. Now, if I want a basis for this span, if I want a basis for the row space, what I could do is figure out which ones of these are linearly independent, which ones are linearly dependent, throw out the dependent ones if I need it. So what I would do to do that is I would take the row reduced echelon form of this matrix. 2, 4, 5, 1, 1, 1, negative 1, 1, 2. All right? By the way, I want you to notice what this matrix is. What have we done here? I did this on purpose. We've swapped row 1 for column 1 of this matrix that we're row reducing. We've taken row 2 and put it in as column 2 of this matrix we're reducing. So what this really is this is going to be the row reduced echelon form of A transpose. Okay? And you can argue, you can see hopefully, that the row space of a matrix is exactly the column space of the transpose of that matrix. All right, so hopefully you see that. Bang. So let's say we row reduce that. We row reduce that and get this matrix. And so what we have is that the row space is going to have dimension 2, and it's going to have a basis of these first two vectors. So the row space has a basis of, well, goodness, those two vectors. Okay, so the row space would have dimension 2. Now, because the row space is basically identical to the column space of the transpose, we don't deal with it a whole lot in this class. It's something to be aware of, but again, we're not going to deal with it a whole lot. I will mention kind of row space, column space when we get into um, orthogonal sets and orthogonal subspaces and things like that. But that's in chapter 6. So we don't need to deal with that a whole lot right now. What I do want you to take away from this section, though, was obviously rank of A being n, nullity of A being 0 when the A was invertible. Being able to use these logical steps along with the rank nullity theorem, that was the other big issue. So rank nullity adds to the number of columns. That's because the number of columns can be thought of as pivot columns and free variables. Pivot columns all represent basis vectors for your column space. Free variables all represent basis vectors for the null space. So that being able to use logic and then that observation. Okay? So there it is. That is a pretty short section. The next section will be a little more standard.